Okay, right, so LP15. Okay, so we want to find an equation for the plane that's parallel to and equidistant from lines represented by these symmetric equations. Okay, so you know what, I may be remembering that I recorded an answer to a similar question. Okay, so anyway, we'll do this one too. Okay, so let me talk about the strategy first. I'm going to draw a picture. So we have a line there, and we have another line like that, and there's a plane that's kind of, if these are the two lines, there's a plane that's kind of sandwiched right in between them, right? Okay, so, and I'm going to try to draw that plane. So something like that. Okay. Yeah. So it's a tough draw, but here's the idea. If so, I make the claim that if I take any point on the first line and any point on the second line, that if I look at the line segment connecting them, that the midpoint will actually be on that purple plane. That's the claim. Right? So, and this is always the part that students find hardest. Is this what you kind of wanted to hear?
The setup.
Yeah. Okay. So why is it that midpoint? Why is it I can do that? So, neat observation. By the way, I've given different explanations in different semesters, but here's my current favorite. If you look at that vector there, and you look at this vector here, notwithstanding my bad drawing, those are actually the same vector. Right? So let's give it a name. I'm going to call it, I don't know. Let's call it M. I don't know. Okay. All right. Now I want to compute, how far is each one of these lines away from that plane. We've got a line and we've got a plane. I need to know what each distance is because I need to check that they are in fact equidistant. Right? Okay. So, all right. Well, here's that first distance that I need to compute. That first distance is this perpendicular distance there from that line to that plane, and we'll go ahead and write down that formula. You notice that it goes from the line to the plane. Well, this vector here goes from the line to the plane as well. It just does so at some undetermined angle, right? So what I'd really like to know then, this distance, I'll call D1. That is, it's not the length of the M vector, but it's the component of that M vector in a certain direction. And specifically, there's a normal vector for this plane, right? And it's I want the component in the normal vector direction, in that perpendicular direction. That's how you talk about the distance from a line to a plane is, in a perpendicular sense from the plane. Is that happy for everybody? Okay. All right. Okay. So I need to compute that. Now I also need to compute this distance. That perpendicular distance from that blue line to the plane. So that's, break that down, D2. Well, again, that's, from the line to the plane. Well, this vector here goes from the line to the plane, but at some yet to be determined angle. And so what I'm really interested in is the component, the sort of appropriate component then. It's the component of that vector M, but specifically the component in the correct direction, and the correct direction is again the normal vector direction. And so, how do I know that these are equidistant? Well, because the formula for these two distances, same exact formula. It's really convenient how that works out. Right? So that argument shows that if you make this choice, if you choose the midpoint to be your x naught, then they will be equidistant.
Okay.
Cool. By the way, now you can come up with a formula for the normal vector. That's the other thing that you need, of course, to define the equation of the plane. The normal vector, and the way you're going to do that is first find the direction vector for the first line, right, and then find the direction vector for the second line. And you've got the symmetric equation, so you've got to do a little bit of algebra there to figure out what those direction vectors are. But then this normal vector is just the cross product of those. Yeah.
And you can choose any points on those two.
Well, you could, but it's even easier than that. I mean, if you have, let's go back up here to the statement of the question. You have symmetric equations. Real handy way to find the direction vector is to just realize that those three things are t, right? And then from that, solve for x, y, and z, and you'll have x, y, and z as functions of t, and then you can rewrite that as, some, I'll call it c naught plus t v1. And so you can just read the direction vector straight off of there. The trouble with trying to just pick any two random points is that it's hard to find points satisfying symmetric equations, because symmetric equations are testers, not generators. Does that make sense? And so, how would you go about even finding points that satisfy those equations? Yeah. You good?
Mm-hmm.
Okay. All right. Let's stop the